Santiago Royo, from business developer and founder of Beamagine, and he will tell us about high-resolution multimodal imaging for object detection on the sea surface, mixing imaging modes for optimal detection. Santi, please, the floor is yours.
Thank you, Gabriel. Thank you, everybody. It's a pleasure to be here presenting our technologies. We've been presenting some of these technologies in previous webinars, so I tried to make a different approach, and I would like to share with you what are the things that we are doing at Beamagine regarding high-resolution multimodal imaging for object detection in the sea surface, related to maritime environments where we've been quite active last years. We essentially are, or were essentially initially a LIDAR company, so essentially we had an own developed technology, which is pretty special and which has a lot of potential for LIDAR imaging. We've been working in automotive with large companies, and essentially for those of you who are not familiar with LIDAR, LIDAR is essentially something which then laser pulse of light onto the scene, and then counts the time it takes to get the target and get back, and from that time you get the distance. If you then scan over the whole surface, you're able to get the 3D image. And here we have some examples. We have the example of the scene we see from the window of the lab. And then you can see the 3D image coded in depth. And here we have the 3D image coded in reflectance of the objects that we are seeing. These are the typical outputs that we are getting when we speak of LIDAR. Our main contribution or main novelty is the type of component that we have, which has developed a technology which is licensed to automotive and which has essentially this main 4 key points. We are able to develop something which is especially good for managing solar radiation from the front of the LIDAR. Of course, you have to manage your LIDAR to go over the background noise that the sun is providing you, so you have to be very good at filtering out the sun background light that you get. That's key of the patents that we've been bringing on. And the other side, as you saw before, we're able to deliver very high resolution. We can get images at 0.05 degrees of angular resolution between point and point, both horizontally and vertically, which goes much beyond what's needed. Just to have an idea, you may see here below, which is the typical case of the automotive detection that we are asked to fight, which is detecting something which is 100 and something meters away with 10 centimeters of height, which is the amount of height that you have in the bumper. So you have to manage with this type of objects, and in particular they are tires, so they are black. You need to have very, very good detectivity, and you have to be very precise stripping and getting the detail of the image. Afterwards, we'll see one video related to that. Furthermore, we managed to have the system being solid state, being able to manage long ranges up to 100 meters without many problems, with very low reflectances, at 10% reflectance, 100 meters. And then we are also 1 +1. So we managed to have a very good LiDAR, and we started to work in automotive. And then we noticed, sorry, I'm not able to. We noticed that in automotive, people had a very, very important problem in the fact that when they were trying to fuse, cameras with 3D in the autonomous car, they are trying to have cameras plus LiDARs plus ultrasound plus whatever, radar. And then with the cameras in particular, they had a very special problem, which was the fact that they needed to post-process continuously the 2D images in order to make them match with the 3D images because of the parallax errors they have. And you may see it in the image above. Fields of view are different, frame rates are different, misalignments are present, vibration happen. So it's very complicated to manage to have a stable data fused from the 2D and the 3D side at the same time. And that's something with the technology that we have is very easy to implement. So we managed to do that. And now we are able to offer systems which are LiDAR and at the same unit some other imaging modes, which can be one or up to three different cameras. We work in RGB, in near, and clear, in polarimetric cameras. We'll see a lot of polarimetric images afterwards, like the ones you have at the side, because these polarimetric images are especially useful at the sea, as you may imagine, because of the polarization properties of the reflection of the water. And we've also worked with hyperspectral and thermal. And managing to fuse all these modes is something, all these modes, or some of them, is something which has been very practical and which has enabled us to gain some customers. You may see here the data. This is the polarimetric camera image, and this is the 3D overlapped onto the polarimetric camera image. So each of the spots of the LiDAR has also the complete polarimetric information, which includes angle of polarization, which includes degree of polarization, which includes intensities at different length, at different orientations of the light of the image. We can do that at different types of images. The most demanded normally is working with some kind of combination with RGB or CCTV cameras. So you are able to fuse the 3D point cloud perfectly with the RGB image. So you can have all the information of color and depth and reflectance in a single image. That would be one of the possible approaches. The other one is the one that we were commenting before, the fusion of three-dimensional images and polarimetric degree of linear polarization or angle of polarization, depending on what you want to look at. And also we've done that for thermal, where here you may see that we are fusing the thermal image of the camera with the 3D image that we get from the LiDAR. So we got temperature information and all the spatial features with depth and reflectance that we have from the LiDAR. So it's something pretty useful and pretty convenient. Of course, we are here speaking of maritime, so we have to move away from the typical automotive approaches, and we wanted to, of course, analyze which is the cases for the scenario definition. And maritime, in our case, has been something that had needed an adaptation. We need to adapt that because, okay, there are radars, there are image processing, there's not much LiDAR. But in practice, there's a problem which with LiDAR you can manage very well when you are working with unmanned or manned and autonomous ships that are working at sea, which is the problem of floating objects around or close to the vessel at the sea. Collisions are still something which is pretty dangerous at sea, and there's a lot of floating debris like this container we see here, but also we may want to detect somebody who has fallen in the water. And preventing collision and detecting objects which are oversea is something which is pretty well performed by the system that we have. We focus on the small objects, which are the most complicated to detect with conventional radar approaches. So you can have some capabilities of detection that are improved. And now I will show you some videos of what can be done first on the automotive. This is the first video that we have. You may see it's real time. That's down is the video, above is the polarimetric images, and at the right you have the LiDAR image fused with the polarimetric data. And there I've placed a 10 centimeter hard tall car box. That's 10 centimeters tall. You may see that we are moving far away from the object, and it's hardly seen in the images, but you are still able to detect that. There we are losing it. And we did that, and it was working at 7 centimeters of distance, and you are able to detect perfectly the box by using the combination of polarimetric and polarization image that we have. So you are pretty good detecting and improving the detection of both systems by combining the features that both of them do. If we look into water, it's even better because, of course, the angle of reflectance of the light is very well determined after the reflection on the sea. And then if you combine polarimetric imaging, you may see that the water has clearly one angle of polarization, and the rest of the image has a completely different angle of polarization. So if you have objects which are over the sea, like these rocks, and we will see later, you may see how we are able to see them pretty well. Okay, you may see that the rocks are perfectly getting out of the water. You may detect them pretty well. And you may see that these three rocks are the three ones here above, and the three marked these three ones, and the only one of these three in front. So it's pretty easy to detect small objects in front of the sea, in front of you when are slightly over the water. That's the first approach. That's a small object floating on the object. That's a buoy, which some of our people hailing the buoy and taking it out. You may see that you can see the 3D image, so you know exactly where the buoy is. And you may see it is there because it's very easy to detect because it's very much easy to see from the background that you have from the LiDAR image. So you can manage very well to detect this type of small objects around the sea. And, sorry, I want to move forward, which is this way, yes. And then we have the case of a person. If you want to are working in some kind of rescue mission, or if you just, I don't know, are in a cruise and somebody falls to the water and it's in the middle of the night, you still have the LiDAR in the middle of the night, and you can try to detect that guy perfectly, whatever gets over the surface of the sea, by looking at the combination of the LIDAR and the polarimetric image. The LIDAR better at night, the polarimetric image better by the day. So it's a pretty useful system. It's working very well. And you may see that, well, those are pretty. Okay. So currently what we have is something like a customized approach. So depending on the application, we deliver one type or other of combination. At the maximum combination, we got everything. So you can have a LiDAR, you can have a CCTV camera, a thermal camera, and a polarimetric camera. In all of them, all of this is packed into something which is pretty small, which is 10 by 20 by 20, essentially. And from there, we are able to deliver up to 12 different imaging modes, both passive and active, day and night, because each imaging mode is complementary to the other. It's managing bad weather quite well using the polarimetric and the thermal, but that depends on the type of application that we want to tackle. We got software, perfection software for human-made for human detection. We are able to detect small cross-section objects. We got the diffusion and AI embedded inside of the system, and essentially we got an integrated user interface, so you can just put it and play, and ESK. Software for integration working perfectly in Windows and Linux. You can choose which is your option. Contact us and we will be able to deliver something for your application which works very well. These are the typical use cases we've been sometimes contacted by for maritime. Short mid-range obstacle detection is the first one. Path planning for risk avoidance is complementary to the first one. Sometimes it's used for close proximity navigation, or for automated docking in harbors. And essentially, as you may see, it's anti-contact or anti-collision, which is the main application that we are finding out. Of course, we can have that as part of the infrastructure if it makes sense for some applications. And it's something that we have been doing for the last year. So we are able to deliver systems with, I don't know, all types of fields of view, all types of ranges, and all types of configurations with 2D images. So it's pretty easy for us now to configure something. So that's it. Thank you very much. I think I got into my time. Thanks for all your interest. And if you are coming by IFSEC in September or by SECON in Korea next July, hopefully, we can see there and we can show you our things, our systems at work. Thank you very much.
Thank you for this very interesting presentation. And now we start with questions. First one from Pepe. Which is the minimum size this LiDAR technology can detect on the sea? And all kind of materials like plastics?
10 centimeters in practice. Oh, in practice with plastics, it's also something which can be used, yes. It was something we were thinking about. Mm-hmm. Around 10 centimeters.
Okay. And next one from CPN. Could you provide an estimation of the energy consumption and space range of this LiDAR technology?
The space is roughly, as I told you, is 10 by 20 by 20 now regarding space, but that includes the 3 cameras, so possibly it can be a bit smaller. I believe we can do it by 10 by 15 by 15 centimeters. That would be space. And the other question was energy consumption. We are around, I now don't have a unit with only the LiDAR, but with the LiDAR and the cameras is the less consumption. And it's about 20-something watts.
Mm-hmm. Okay, next one from Joachim. Does any of your technology apply for subsea imaging?
Well, the technology could work for subsea imaging exactly the same one if we do the proper adaptations. First of all, we would need, of course, to survive under the sea, which depends very much on the ability to build enclosure. And of course, we will have to adapt the optical design and the wavelength. But beyond that, I don't expect many issues. All the technology could be used under seas in principle.
Great, because as I see, we have some interest here in the capacity underwater, because the next question is about. And what are, from Luis Orihuela, what are the computational needs for processing the images and fuse images?
We are delivering the hardware as a point cloud for the moment. And we have some software for developing, for making some identification of pedestrians that we work in the software that we have. And currently the system gets out of the data gets out of the system with an Ethernet cable, and we manage to compute it. Regarding the getting the point cloud, it's something you do seamlessly. You don't notice it. It's real time in frames per second. Then depends on which type of processing you want to make and how precise you want to make it, and depends the approach you take. You can start with 2D, go for 3D, or start with 3D. Depends on the approach you want to make. But currently we work it with simply a jet on board with the pedestrians. It's not extremely complex, but it's not extremely demanding. But you need to be careful on which type of application and how you use your data, essentially.
Mm-hmm. Okay, thank you. Now, straight to the point from Serasio Avornio. What's the average cost?
Depends on the configuration, but typically the average cost is about 15,000.
Mm-hmm.
It depends on the configuration. Can go down if there are no cameras. Can go down if you get something which is doesn't need to get much longer ranges. If you don't want to get to 100 meters, you can downgrade the source, and then you can have cheaper approaches. Mm-hmm. Depends on the application. What we are doing is to reconfigure that typically, but this is the average price that we are having.
Okay. The average cost in dollars.
In dollars, it's about the same. It's the approximation does include the change. I would say 15,000 could be something like that.
Okay. So I think that we have no more questions for now. And also for me, thank you very much, Santi, for your answers and for your presentation. Those questions also clearly demonstrate to me that we have really international audience here, and we are going beyond Europe with this dollar question. Okay, so that's all regarding LiDAR systems, and now we will go to our next presentation,